So here we have our proteins. So they're the most abundant organic molecules in living systems. And what they do is they help undertake metabolic reactions. So as we see here we've got these two molecules which we call substrate A and substrate B. Now for them to form a product naturally without an enzyme may be very slow to occur or maybe not even possible. It's only through the activity of an enzyme that we can speed up or enable this reaction. So as we see here we have an enzyme which is made up of all these different amino acid side chains which determines the form and the function of the enzyme. And here we have the catalytic site where the reaction joining substrates A and B in this case to make the product occurs. So we can simplify this down just to show that the catalytic site is actually determined by all these different amino acids which line it in terms of that will determine what it can and cannot bind. So as we see here, so the enzyme can bind these substrates within its catalytic pocket, undergo a reaction to then release the product. Obviously enzymes, in addition to making molecules, can also break them down. So in this case we see that the enzyme binds the substrate, catalyzes it and then releases two products, product A and product B. So it's quite the reverse of what we've just seen. Now of course this can occur at a very rapid rate. Some enzymes have a catalytic rate of 2 to 10 cycles per second, whereas some undertake their catalytic rates really fast, such that they can do 10,000 reactions or more per second. So we can see the benefit that nature has enabled to speed up the reactions at which this occurs. Now what determines whether a substrate will bind to an enzyme? So this is what we call the substrate specificity. So this is obviously influenced again by the amino acid component of the enzyme. So these can determine the size of which the enzyme preferentially binds, such that a substrate that's too small won't bind or be catabolized, or if the substrate is actually too big for the catalytic site, nothing will happen. Obviously, if the substrate is also of the wrong shape, such that it doesn't meet the shape requirements of the enzyme, it too won't undergo catalysis. And so even though it may bind it, the catalytic reaction won't occur because the substrate shape is not compatible. What can also happen is sometimes during evolution, amino acid changes can occur within the active site, as shown here, and we get a substitution with another amino acid. What this does though is it'll change the shape of the catalytic site and therefore no longer making it compatible with what its initial substrate was. So you won't get any catalytic reaction occurring. Obviously the charge of the amino acid residues and their side chains within the catalytic site will also influence the binding potential of a substrate. Now of course some molecules which look like the same substrate but actually don't have matching charges will actually be incompatible for the catalytic reaction, and so therefore catalysis won't occur. So this is how we build up an enzyme substrate specificity.